Good morning, everyone. Welcome to the EasyPower Tuesday Refresher webinar series. My name is Jim Chastain. I'm an applications engineer here at EasyPower. And we appreciate your attendance today and spend a little bit of time with us talking about some, in this case, protective device coordination and the features in EasyPower that enable us to do a better job of that function. As you may have can tell by the title, we've actually made this a 5-part series. This is the second part in that series. And what we're talking about when you look at the EasyPower module lineup is the power protector module that does the coordination function. And so we will be focusing on the capabilities and features and hopefully making your job easier in the process because of the information that you can derive by using the tool. As we like to begin each session with a poll question, give everyone a little bit of time to settle in and maybe get a handle on what the perspective of the audience is. We have a couple poll questions for this morning. Again, so the first question is, how often do you coordinate breakers in an upstream from an MCC? Again, this is one of the topics we were going to focus on today. And frequently we get questions about how the interaction is between the different devices in the process of doing coordination. So we will spend some time on this. Here's how folks have weighed in on this topic. So it looks like it was a pretty even split across the board. All right. And then the next question is, what's your preference as far as motor protection in general? And this is a multiple choice question, and there's really no right or wrong answer, just getting some feedback from the real world where the rubber meets the road. I oftentimes enjoy talking to customers and EasyPower users in the field because they are having to deal with the actual application of the tool in their situation. And so there's not necessarily a right or wrong answer. It really boils down to what does the job best in your situation. All right, so here's how folks weighed in on this one. And yeah, I'm not surprised. Actually, I appreciate the confirmation of what my assumption has been. So again, thank you for participating. And let's get on with the discussion. So last week, a question came up that I purposely, or not last week, although actually it did come up last week, but the last session, a question came up that I wasn't prepared to answer because it referred to a specific article in the National Electric Code. So I wanted to start off with that as the first discussion point. And then we're going to be talking primarily about motor protection, load protection, and use of the TCC plotting tools in panels and MCCs. So the question that arose last time is regarding NEC 51731G, and the question was, does a safety system, an essential electrical system, need to be coordinated? And so this is what the article 517.31G says, and it struck me as an interesting paradigm for someone having to deal with this situation. So if we go into EasyPower, and my focus here is not to answer the question as far as safety devices or protective systems, safety wiring systems, but to show what's available on the TCC plot to be able to use to answer the question. So I'm going to pull up the motor itself. We're in the coordination module of this very simple one line, and we're going to plot the TCC curves. So the question is, if we look at it again, that the overcurrent protective device essential electrical system shall be coordinated for the period of time that a fault's duration extends beyond 1/10 of a second. Well, that doesn't make any, it's difficult to answer the question until you look at the TCC curve itself. And so again, what we're looking at is a plot of time on the vertical axis and current on the horizontal axis. And what's being asked is, okay, if there's any fault that lasts longer than 1/10 of a second, I need to coordinate above that, or at least that's what that article says. So if I look at my log scale over here, I see 1/10 of a second right down here close to the bottom. And if I go across, then any current at this point potentially would cause a fault that lasts 1/10 of a second. So what I read in that article is that any protective devices that we have in series with this load, this sensitive load or this critical load, if a fault occurs at this current, then I need to be coordinated. Now, let's take this a step further. If I go, so we'll come back to that in a second. If I look at NEC 695.4b, and again, I'm not an expert in fire pump design or electrical system design when it comes to safety systems. I'm just reading the articles. So in 695.4b, it states overcurrent protection shall be provided by assembly listed for fire pump service and complying with the following. The overcurrent protective device shall not open within 2 minutes at 600% of the full load current of the fire pump. The overcurrent protective device shall not open with a restart transient of 45 times the full load current for the fire pump. And the overcurrent protection device shall not open within 10 minutes at 300% of the full load current. Okay, what does all that have to do with us? Again, if we look at this log scale, we have 10 seconds on the vertical axis, 100 seconds, and then 1,000 seconds. And so we want a protective device that will allow the motor to run at those levels. If we look at the bottom end of this little thermal damage curve, this short stubby plot is the stall curve where we can get thermal damage on the motor. If we open up the motor setup tab, that plot, thermal plot, is indicated by this little checkbox. Let me slide this over so we can see everything. All right, so this plots that little stubby line, and the bottom of that line is dictated by the settings here. So it's currently set for 6 times full load current of the motor as we set it up, and this right here ends up being that 6 times FLA. If we had used a different multiplier, I'm going to change this to 12, watch what happens to our curve. So it moves up that current for the 6 multiplier and for the starting current of the motor itself. So what this article is saying is the protective device, as we set it up, has to allow the motor to run infinitely or unlimited amount of time at that point. So let's go back to our full circuit and look at our protective devices. So I'm going to go ahead and include both a main breaker and plot the curves. All right, so what this shows, we have a mag-only breaker set up for motor protection. And if we expand this a little bit, we can see that this motor protection device will not trip no matter how long we remain in that condition, considerably above the 6 FLA maximum current point. So for a selective device, this kind of deals with what we're asking for. Now the point about coordination, again, this would be if I have a main breaker for the whole system we would want it coordinated at any fault that falls above 1/10 of a second. 1/10 of a second is this line right here. And if we take this over to that current at 6x FLA, 1/10 of a second is right there. And what the slide said, the first slide said, is that we need to be coordinated above that point. Well, the way we have this currently set, it's coordinated for some amount of time out to at least this point here where we have miscoordination. Now, again, I'm not saying that this is the way to design the system. I'm just pointing out how to read the information off the plot. So we've selected a mag-only device that is sized to protect the motor and the current. The current won't melt as long as the current melt the cable, as long as we stay below this curve. And so in terms of the NEC 695 condition, this is motor protection that will allow the motor to run indefinitely at 6x, better than 6x FLA. And the way we've got this set is that for any fault, and so the point I'm trying to make is the fault current isn't out here where I fault this bus. The fault current that we're talking about is what's going to occur at a tenth of a second, and that would be currents, low currents. In this case, less than 1,000 amps. I'm looking at 100 times 10. So at a tenth of a second, anything less than 1,000 amps would be allowed, and we'd be coordinated between these two devices. Now, I'm sure that didn't make a whole lot of sense, but to answer the question, the original question was, do we have to coordinate protective devices on a safety essential electrical system? The answer is yes, on any current that will extend a fault beyond a tenth of a second. And so the information is on the plot. We just need to be able to look for it. And then secondly, do we want overcurrent protection on a fire pump? In general, you want the fire pump to run as the last load in the circuit is still alive. And so these conditions can be met as long as we stay within the 600% of the full load current. Okay, I'm through with that one. If there's any questions, by all means, shoot them at me. It's a fun discussion, and my point is there's a lot of information on that plot that we don't usually get to. Okay, so the thing we didn't complete last time was talking about more aspects of the TCC plots, specifically talking about subsystems and motor control centers. So that's why I want to spend time now. And if we close this puppy out, to me, it's actually fairly exciting, not just to use the tools, but realize there's a lot of information that we don't necessarily ask for in the first round, but it's available if we just know where to look for it. So I want to look for my MCC example. Now, there's one disadvantage in using an MCC icon or a motor icon or a panel icon if you're going to calculate arc flash incident energy. And that is, when I'm using an icon and I go into short circuit and fault the bus, the calculations are being made to the main bus on the MCC and the panel. And so what I'm missing at that point is the ability to label loads, put a label, an accurate label on downstream loads. Now they can be calculated and shown as far as coordination by the tools, even if I've got them embedded in the motor control center specifications. So if I go back to database edit and I open up my motor control center 1 here, we've set up incoming if we're going to use a main breaker as opposed to a main lug or a main fuse, we'd use this element to set up the incoming devices, the incoming device parameters. And so here we're setting up a molded case circuit breaker with a solid state trip unit. And again, once I set the part number up, I want to make sure it's in the device library. So I click calculate, and then I have these parameters set up. Now what I don't want is an instantaneous pickup, because that's a function of the downstream breaker. So this is the main on the motor control center itself. Then when I go into description, to be able to coordinate against the largest load, I need to designate it in my motor control center spreadsheet with the motor TCC designated load, as opposed to a motor or a downstream device. If I want a label on this motor, I can designate it as a downstream on the one line and then be able to pick up a label at that point. But for now, I just want to be able to coordinate. So now that I have this set up for my motor with a TCC plot, I scroll over, and instead of entering the parameters for my motor here, I use the data dialog box that allows me to put in the parameters just like I would for that individual motor. And again, we'd set up the horsepower. If we want the full load current, we could click on this calculate button. If we leave it blank, the kVA rating will be calculated with the efficiency, power factor, and kilovolt rating. So this is the motor data itself. Now if I want to, so then I click calculate to get my TCC, my X over R. Now that's the motor specification. Likewise, the breaker has to be set up separately. Normally in the spreadsheet, I'd set up the parameters here. If I have a specialized load, then I'd use the setup for the breaker just like I would a specific breaker. And we're going to set up part number, verify that it's in the library, look at the phase settings, and then for coordination purposes, we're going to want to plot the overload and specify that. And when we get back to and then likewise for the cable needs to be set up separately, just like I would an individual cable. So now that I have the motor set up, I can go into the TCC plot of power protector. And what we see are a number of devices. So the thick red line is the motor parameters, the starting curve. I want to put in the BL1, which is the main breaker at the top, is the last one to trip. MCC1, row 1, is my mag guard, which is going to be a magnetic only instantaneous trip, is going to be tripping first. And then my main breaker in the motor control center is going to be tripping third. Now, the part that I wanted to emphasize is the importance of a motor overload relay. Because if I just set this up without that in there, my plot for my mag-only breaker is not going to be coordinated with anything. And if I look at the thermal damage curve for the motor, we're going to be not having protection that falls inside of that motor overload. So to deal with that, we need to make sure we use a motor overload relay with parameters that the manufacturer assures us will fall within the motor damage curve. And consequently, we can coordinate the upstream breaker along with our main and the mag-only protection on the motor itself. Now, as I indicated, the only downside to this is that it will not give me a label, a printable label. And so I can either put labels, go back to my short circuit. Look at half cycle current, fault the buses, and look at instant energy. I can see that under the way I have things set up, I can include the main in, or I can do both include and exclude and see what the calculations for upstream of the main and downstream of the main, which I might use for labeling the buckets, the rest of the buckets, and then put this label on the bucket for the main breaker itself. Okay, so the point I'm trying to make is that we can coordinate embedded motors in a motor control center. We can put multiple curves in there, but we really get the benefit from the largest load as far as instant energy calculations. But surely if I wanted to plot multiple loads, I could save the TCC curves for each one and verify that I looked at those as we went along. Now, as I mentioned earlier, we could do the same thing for a panel, except a panel doesn't have the ability to model a TCC. Let's just kind of put a panel on here. So a panel doesn't have the ability to model a motor with the TCC curve. So again, I can set up a motor, but the calculations are only going to be for the main bus. But it will include motor contribution. So if I have a load that I want to generate a label for off of a panel, I'd separate a subsystem and connect it to a particular circuit in the panel itself, and then put the motor that I want to label out here with characterizations of the details of the motor. And then we could plot the TCC against the parameters of the breakers inside the panel itself. Okay, so what are we doing here? We've covered subsystems, how to set up and coordinate with breakers inside the main and the dedicated feeder for the largest load. Although we could do each motor in the system if we wanted, it would be relatively confusing as we were trying to do coordination. So the largest one would suffice if coordination is what we're trying to achieve. And then the disadvantage is that we're not going to have a label for any particular downstream load, but we can use a generic label printout by using the detailed setting showing upstream with and without the main for the MCC. Okay, and then we also talked about the information that's available for doing unlimited lower current. Well, that was the other thing I didn't mention on the infinite time or the unlimited time to run at greater than 6 times full load current. Why would I care about that? Well, for starters, a full 3-phase bolted fault would shut everything down, whereas if I had a very low resistance fault, it could potentially trip a breaker if it was set too low. So that's the purpose on coordinating on lower current than the full load faulted bus 3-phase bolted fault load. Okay, so the other thing we didn't get to is the ground settings. We'll start off with that next week, our next session. We divided this up into 5 periods or 5 episodes, and we'll pick up with a discussion on the ground settings and then looking at phase settings and ground settings simultaneously. If you got questions, by all means, shoot them at us, and and look for the schedule on the subsequent presentations. Thanks for joining today. Stay safe.